In this video, we will see how to model turbo machines when developing a system model for a power generation or propulsion application. First of all, let us clarify what turbo machines are. We classify as turbo machines all those devices in which energy is transferred either to or from a flowing fluid by the dynamic action of one or more rotating blade rows. Basic components of power generation and propulsion systems, such as turbines, compressors, fans, and centrifugal pumps, are then turbo machines. Different methods can be adopted to model a turbo machine. The main ones are listed in the slide in order of decreasing accuracy and computational complexity. We have CFD-based methods, where the Navier-Stokes equations, together with the continuity and energy balance equations, are integrated over multidimensional domains, making use of proper numerical and modeling approximation techniques. This method is clearly not suitable for predicting turbo machines' characteristics in a system model, given its computational complexity. A modeling approach which entails a much lower computational cost than CFD is the mean-line method, where a turbo machine model is formulated with a lumped parameter approach, only focusing on inlet and exit conditions of each blade cascade, regardless of the detailed shape of the blade. At the considered locations along the machine, uniform and unidirectional flow is assumed. The tools to build such a model are the balance equations of mass, energy, and momentum, alongside an empirical loss model to evaluate entropy generation inside the blade channels. Thanks to these dramatic simplifications, the mean-line model allows for quick determination of fluid dynamic evolution over the entire machine. For this reason, mean-line models are used during preliminary design of turbo machines, namely to get an estimation of the main dimensions of the machines, like the average diameter of the discs, the blade heights and axial chord, and so forth. However, these kinds of models are seldom used in off-design analysis or dynamic simulation of propulsion and energy conversion systems. The reason is that they are still too computationally expensive for system simulation, especially in the case of multi-stage machines. Turbo machine characteristics are instead taken into account in system simulation by using maps, which describe how the characteristic parameters of a machine, like isentropic efficiency, mass flow rate, or pressure ratio, vary over its operating envelope. This approach enables very fast computations, theoretically guaranteeing at the same time high accuracy. The maps are most of the time derived experimentally, or with a combination of experiments and numerical simulations. By applying similarity rules, the obtained maps for one specific machine can be also extended to other ones, provided that these have similar geometry to that of the tested machine. Performance maps can also be evaluated in the preliminary design phase by using a mean-line model. However, reliable estimates are obtained only if the 1D model has been validated and empirically tuned upfront for the specific application under consideration on the basis of experimental data. In the following slides, we will see what these maps look like for turbo machines. Let us start with turbines. The characteristic curves of turbines are usually reported in charts which have on the vertical axis the corrected flow, also called flow coefficient, while the pressure ratio on the horizontal axis. Different characteristic curves do exist, depending on the corrected or specific rotational speed of the turbine. The corrected speed is defined as the ratio between the actual rotational speed of the turbine and the square root of the inlet total temperature of the turbine. So the turbine characteristic curves are mapped according to three parameters: the corrected mass flow rate, the corrected speed, and the pressure ratio. Maybe you already know these quantities from other courses dealing with turbo machinery or aero engines. The expression for the corrected flow and speed can be derived based on similarity rules. If you are interested in the demonstration, I refer you to Chapter 2 of the book Fluid Mechanics and Thermodynamics of Turbo Machinery by Dixon and Dole, from which I have also taken the chart in the slide. Anyway, to understand the rationale behind the use of these corrected quantities, notice that turbines deal with compressible flows. So, by scaling mass flow rate and rotational speed with respect to total temperature and pressure, it is possible to take into account of the variation of density with pressure and temperature, as well as of the variation of the speed of sound. In this way, the characteristic curves are made independent of the specific inlet conditions of the turbine, where they are calculated or measured. Looking at the chart that belongs to a two-stage axial turbine, we can notice that all the characteristic curves have a similar trend. The flow coefficient rapidly rises for increasing values of the pressure ratio. But when the pressure ratio exceeds about 2.5 across the machine, the different operating curves become more and more independent of the rotational speed, and they tend to converge towards the same value of flow coefficient. The reason is that as the pressure ratio of the machine increases, one of the turbine stator rows chokes. Then the mass flow rate cannot further increase with the pressure ratio, and the flow coefficient becomes constant. A similar trend is found also for turbines with a higher number of stages. Although for a given pressure ratio, the flow coefficient tends to decrease with the addition of further stages to the machine. At the same time, the choking pressure ratio increases. It results that the characteristic curve of the turbine becomes more and more similar to an arc of ellipse as more stages are used. The curve of a multi-stage turbine like that in the diagram, namely with at least 5 or 8 stages, is indeed well approximated by the so-called ellipse or Stoddard law, after the name of the researcher who first proposed it. You can find in the slide its expression, where the subscript 0 in front of the state point number indicates total conditions. The constant K in the formula can be determined knowing the operating conditions of the turbine at the design point. The Stoddard law is often used to model the flow characteristics of steam turbines, because these turbo machines work generally at a fixed rotational speed, as the alternator, driven by a steam turbine, is connected to the electric grid, which has more or less a constant frequency. So, for a steam turbine, the flow characteristic reduces to a single curve in the flow coefficient versus pressure ratio chart, which can be easily predicted by means of the Stoddard law, after proper calibration of the parameters. This is generally not the case for gas turbines or turbofan engines. First of all, gas turbines have less stages. It means that the Stoddard law will be less accurate, as the turbine characteristic curve's shape will deviate from that of an arc of ellipse. Second, the reduced speed can vary quite a lot over the operating envelope of a gas turbine of an aero engine. So for aero engine simulations, the flow characteristic is modeled by 2D maps, which are determined by experiments or numerical studies. The 2D maps are coded in a model as matrices. A 2D map can be defined also for the isentropic efficiency of turbines. In the slide, you can see the trend of isentropic efficiency versus expansion ratio and reduced speed. From this chart, you can notice that turbines can be optimized at part load by changing the rotational speed. In theory, the performance of the machine can be kept very close to that of the design point over a wide range of expansion ratio values. Unfortunately, the rotational speed can be generally actively regulated only in small capacity turbines. Regarding compressors, their characteristic curves look much different from those of a turbine. First of all, compressor part load performance is typically presented in charts with the pressure ratio on the vertical axis and the so-called corrected flow on the horizontal axis. In the figure on the left-hand side of the slide, you can see the performance map for a transonic fan. Instead, the chart on the other side of the slide shows a performance map for a high-speed multi-stage axial compressor. Both figures also show contours of the isentropic efficiency over the compressor operating envelope. As expected, the compression efficiency decreases as we move farther away from the design point of the compressor. Differently from turbines, the different isospeed lines, so the operating curves of a compressor for a given value of the reduced speed, keep far from each other in the feasible operating region of the machine. Each isospeed line extends between two operating limits. The limit on the left-hand side corresponds to the point of intersection of the isospeed curves with the instability line, which is often referred to as the surge or stall line. Beyond this point, the operation of a compressor becomes unstable. On the right-hand side, the curves end in the choking point, where the flow within the compressor becomes choked, and thus the corrected flow rate cannot further increase. As you can see, the isospeed lines can become very steep in proximity of the so-called choking line, especially in a multi-stage compressor and the high values of the flow coefficient. Compressor maps in the form they are shown in the slide have two main drawbacks for system simulation. First of all, the isospeed lines do not cover the same range of pressure ratio and flow coefficient. Keep in mind that the flow characteristics need to be coded in the model as a matrix to allow for a numerical interpolation. If the rows and columns of this matrix represent a given value of the flow coefficient and the reduced speed, or even the pressure ratio, many elements of the matrix will end up having a not a number value. This will make the interpolation of the matrix very difficult for the numerical solver. The second drawback is that the trend of the characteristic curves is not monotonic. This implies that two possible values of flow coefficient might exist for a given pressure ratio and reduced speed of the compressor. Moreover, close to the choking point, the interpolation of the curves would be very sensitive to the value of the flow coefficient, as the slope of the flow characteristics tend to infinite. The numerical trick that can be used to solve these issues is to introduce an auxiliary coordinate, beta, and define the so-called beta lines or R lines. These lines are parallel to the surge line and evenly spaced to cover the entire operating range of the compressor, from the surge line to the choking line. Each beta line is identified by a specific value of beta. As you can notice from the figure in the slide, the beta lines have a monotonic trend. Thus, for a given compression ratio, they identify univocally the corresponding flow coefficient value. Last but not least, if we now imagine converting the beta lines map in a matrix whose rows and columns represent the auxiliary coordinate beta and the reduced speed, it's easy to figure out that this matrix will not feature not a number elements. Each beta reduced speed pair identifies a given value of pressure ratio and flow coefficient. This approach is implemented both in the software GSP and the Modelica library basic aero engines you will familiarize with in part B of the course. The only drawback, due to the use of the auxiliary coordinate beta, is that two matrices are now needed to map the beta lines. One for the pressure ratio and one for the flow coefficient. Regarding turbine maps, it's worth pointing out that the use of the beta lines is not strictly required. However, often in simulation software for the gas turbines and aero engines, these are used also for turbines to adopt for consistency the same interpolation method for turbine and compressor maps. This is also the case of GSP and the Modelica library basic aero engines. The use of maps to model efficiency and flow characteristics of turbines and compressor significantly simplify the modeling of these components for system simulation. In the slide, I summarized the main equations of a possible turbine model. The conservation equations are purely algebraic and very simple. The main constitutive equations include the definition of isentropic efficiency, which allows for the calculation of the mechanical power. We have then three equations for, respectively, isentropic efficiency, flow coefficient or corrected mass flow rate, and pressure ratio, where these three quantities result from the interpolation of a matrix given the value of the reduced speed and of the auxiliary variable beta. In addition to these constitutive equations, to close the turbine model, you have to consider the relation defining the reduced speed, the equations to calculate the thermodynamic properties of the fluid, and the equations defining the model interface. In this respect, I invite you to have a look at the code of the models for turbines and compressors in the Modelica library, basic aero engines that you can download with the exercise of Module 7. I conclude this video discussing how the fan of an aero engine is usually modeled in software for system simulation of aero engines. Fans of modern aero engines have a very large diameter, so the performance of the fan changes appreciably if you consider a flow section close to the hub or the tip. Moreover, the flow is split into two streams downstream of the fan. A portion of the flow, the core flow, becomes the combustion air, while the other goes into the bypass duct to generate thrust. So the general modeling approach, as you can see in the slide, for the fan consists of using two compressor models. These are connected in parallel with respect to the airflow, and they are mechanically coupled to the same shaft. Each compressor model has its own performance maps. In the schematic of the fan reported in the slide, you can also notice a splitter downstream of the air inlet. Keep in mind that this component is not strictly needed in Modelica, thanks to the features of connector variables. The inlet of the two compressors can be directly connected to the outlet of the component air intake. Automatically, the Modelica solver considers a mass balance and energy balance for this kind of connection.